If you ever noticed a bookshelf with books on it, over time, especially a cheaper bookshelf, that shelf is going to start to sag in the middle. That sag is called deflection. We're going to need to investigate that amount of deflection, in particular for something like a ceiling with plaster on it. If our beams sag too much, that's going to cause the ceiling to start to crack. And that's the ratio we're going to use in this section called deflection, which is our length times 1 over 360, or just length divided by 360. So if you go to example 4, we'll run through one of these deflection investigations. So our first step, I already put in my givens for this example, which is a 20-foot beam with 40,000 pound distributed load. So our first step is to calculate our maximum moment. So if you go to Unit 3 text and go down to the table at the bottom, that equation for our maximum moment for a unified distributed load is case 2, which is our maximum load equals our total load, the big W, times length divided by 8. Let's switch back over to our sheet here, which I've already put into the example portion of the Excel file that I'll be providing. So I'll take our total load times our length in inches, because we're going to want inch pounds, divided by 8. And then from there, now we can solve for our section modulus, which is our maximum moment divided by allowable bending stress. So equals this divided by the 24,000 psi, because we're still going to be using the A36 steel. And so our section modulus is 50 inches cubed. In the text, they're going to use a 14 by 38. When I go back over here and kind of filter that out, there is actually a lighter beam. So I'll go filters between, I'll put 50 here, and then let's just go about 10 above that to give us a good selection. And you can see that we have a 35 pounds per foot, which is the 18 by 35. But let's just continue on with using what they used in the text. So let's just say that for whatever reason, they had a limitation on height. So 18 would be way too tall for whatever they were constructing. So we'll do 14 by 38. So that swap back over here. Scroll down to 14 by 38. Went a little too fast there. There it is. Our reactions, if you can find those with the equation on table 3.1 from unit 3, which is going to be not our reactions, our maximum shear, which is just our total load divided by 2. I'm gonna skip reactions on that. So it's just our total load, because they're the same, divided by 2. Our AW, which is the area of the web of the beam section. So we'll swap over here. Oh, 1 second. I'm going to press equals, click on here, and our web area, AW. So that's a 14 by 38. Click there. And then our shear stress is going to be our maximum vertical shear divided by our area of the web, which is below the allowable shear stress of 14.5 KSI or 14,500 PSI. So I already said that our allowable deflection is our length times 1 over 360, or just length divided by 360. And this is going to be in inches as well. So that is 240 divided by 360. So the amount of sag is going to only be 0.67 inches, which I got that actually formatted wrong. Let's fix that. Okay, we'll put in our moment of inertia. It's a 14 by 38 right here. And then our deflection equation, which is also in the case 2 of Unit 3, the table on Unit 3, or I have it listed out here. It's a little different than the table, but it does the same thing. So we're going to take a constant of 500 divided by 384 times our total load times our length in inches cubed divided by our modulus of elasticity times our moment of inertia. I finished off with my parentheses there, and I must have done something slightly wrong. Oh, I only squared it. Let's make sure I didn't miss anything else here. That should do it. Okay, there we go. So the beam only this particular beam will only deflect 0.64 inches under that load, which is underneath the allowable deflection. So just to kind of visually show it, our deflection is less than the allowable deflection, which is true. So I'm going to jump over to SolidWorks here in a second and show you how to check that with using SolidWorks to make sure that your beam selection is correct. All right, I'm going to show you how to use SolidWorks to check for beam deflection. I got a new file open here, so I'm just going to run through how to do this again. I'm going to select the right plane because that's where I want my section to be. I'm underneath the SolidWorks add-in, and I have the toolbox selected, which brings up these options, and I'm going to click on structural steel. I already found 14 by 38 in the list, but you'll have to scroll through if it's not already selected. I'm going to hit create, and it's going to run through some stuff, and I'm going to hit done. I'm going to get it fully defined. I'm going to select this line, the origin, and I'm going to make it midpoint, and I'm going to make this horizontal. Now I'm fully defined. Exit out of that. In this case, I really don't need to do much more because this is a distributed load, so I don't need any points or anything like that, so I'm just going to extrude it. Extrude, I believe it was 20 feet or 240 inches. So let's just put 240 inches here. Hit the check. Here's my beam. I'm going to go back to the add-ins here, and then I'm going to not go to that and go to simulation because I already have that up. Hit new study. Hit the check. And then run through the process here. So on the first one here, I'm going to right click, treat as beam, right click again, and I've added this to my favorites, A36 steel. Otherwise, click on apply, edit material, come down, find your A36 steel, and then you can right click on this and add to favorites, so you don't always have to come in here. So since I'm already here, I'm going to hit apply and hit close. I'm going to now apply where the supports for this beam are, which is underneath fixtures, which I'm going to right click, fix geometry, and movable, click here and here, because that's where it's supported, and hit check. And then the last step is to apply my load of force. Click on the beam icon, select my entire beam, apply the direction, which is going to be about the front plane, and the load, which was, I believe, 40,000 pounds. Let's double check to make sure that was true. Yep, because that was 20, so 20, blah, blah. All right, good to go. I need to reverse direction. As you can see, the arrows are pointing up. This is a downward force. There we go. Check. I'm going to right click on static, and I'm going to hit run. So as we can see, our bending stress is below our allowable bending stress of 24,000 psi. We already have our displacement on here, but before I click on that, I'll quick just show how to get our shear and moment on there. So I would say this is a good idea to quickly just do these, just so you know that you can see if these are off from your other calculations. You know you have to go adjust something in either Excel or SolidWorks. So I'm going to right click on result, go to define beam diagrams. I'm going to get the shear on there first. So that's shear force in direction 1. Change it to pounds. I have all this set up in my settings to already have the settings I need. So that's good, and I'm going to hit check. So that matches up with our what should be our shear diagram. Right click again, define beam diagrams, and I'll go pounds again. Well, actually, I'm going to do moment about direction 2. If direction 2 doesn't work, try direction 1. But usually, if you've kind of set it up in the way I've done it, direction 2 is the one you want to use. Everything else is set up. I'm going to hit check, and our moment is the same as what we calculated, mostly. I'm going to double click on displacement here, and it's going to be a little bit off, but it's close enough. So double click, and we got 0.669, which our allowable was 0.67. So this should work. I would almost guess that if you got this kind of close, well, obviously if it went over what our calculated was, we're using a lot of rounded numbers with our calculations. So maybe try a different beam, maybe a step up above it, and see what that gets you in the end. So now I'm going to go to another example here with a little more complex load type and show you how to go about that. So I came up with this random problem here where I have a 14-foot beam. I got 3 concentrated loads at some random spots, and then a unified load across the entirety of it. I've gone through, I've calculated my reactions, solved for my maximum shear, use that to find out where my vertical shear passed through 0. Where that happened, that's where my maximum moment was, so I calculated that. So I have done all that, went through, found out what my section modulus was, figuring that out, I selected my beam, and I was able to find everything else I needed to know. What I didn't know is how to necessarily calculate the deflection. If you look at the table on Unit 3, there isn't an equation for calculating for kind of a random layout like this. The math to probably do that accurately is beyond this where we're at right now. So I'm going to show you how I handled this. Is I used case 2 and basically converted the load on this beam into a distributed load. So taking our equation here, m equals w times L over 8, I know my maximum moment and I know my length. What I don't know is big W. So I moved things around. I took my maximum moment times 8 divided by my length, which is how that equation's laid out, which gave me a W of 27,900.29 pounds. Now I can actually plug that number into, let's jump back over there real quick, into this equation. The 5 times W times L to the third divided by 384 times E times I. So my allowable deflection was 0.47, and now my calculated in this using that is 0.38. Now if I check that against SolidWorks, let me see where I put that, I think right here. So I did 2 studies on this. I did the study using the concentrated load and the distributed load to see what my result on that would be. And if I double click on displacement, that's 0.399, which is still below my allowable, which was 0.47. And then I also did a study using my calculated distributed load and seeing what the displacement with that would be. And I clicked on the wrong thing here, and that's 0.397. So similar numbers. So that's the way I kind of got around that, and it seems to work out just fine. So I think there's only one problem where you're going to have to do something like that. So give that a go and see what you get for an answer from SOLIDWORKS, and it should work out just fine.